Hey, welcome back, Chemistry Theory. This is part 2 of the 1.3 electron configurations and the periodic table. So yes, looking at how this all relates to the periodic table and the arrangement there. So hopefully you're able to do this to your pink periodic table. Again, this F group here is actually written down below the periodic table. So hopefully you can enter in all of these just in your first box here so you know the specific rows, what they correspond to. Let's take a look here. Which family of elements is characterized by NS2, NP2 electron configuration? So using up all of the S level and then 2 electrons in the P. So let's see, if we look here, the S ones are used and then 2 in the P. Hey, that corresponds to group 4A. That's so easy. So group 4A would correspond to that. Here, example electron configurations from the periodic table. Based on its position on the periodic table, write the condensed electron configuration for bismuth, which is element 83, and then how many unpaired electrons would it have? So bismuth, and you're thinking, well, it's none of your bismuth. But no, no, no. Let's take a look. So let's see here. It's number 83. So if we take a look, let's see where it would be here. Now, I just have this miniature periodic table in front of me here. So it would be right here, I believe. Let's just double check here. 1, 2, 3, 3 down, 3 over. 1, 2, 3, 1, 2, 3. Yeah, so it's right here. This is where bismuth is. Okay. So we could write the big one starting from 1s2, 2s2, 2p6, or we could just take a look at, ooh, what is this noble gas, which is right before bismuth, and we would see that it is xenon. So we start off with that. So it is xenon, xenon's configuration. So going 1s2, 2s. So notice here 1. And there's the second part of the S. 1s2, 2s2, 2p6. So we'd go xenon, and then let's see where we go from there. Then it's 6s2. So you see what comes next here, 6s2. And then from there, notice how it juts out, and we go into the F block. 4f. 4f14 would be all of that. And then we go back to here to the D region. So let's see, this was 3D, this is 4D, this is 5D, this is 6D. So 6s2, 4f14, 5d10. And then lastly, my P region. So here's my, let's see, 2P, 3P, 4P, 5P, 6P, 7P. So I went back to here, 5D10, 6P3. Look at that. There we go. And how many unpaired electrons? Well, we know that if it ends in the P region, right? So this is, let's say this is our 6P orbital representation. I have 3 electrons. So remember, we put in these degenerate orbitals, we put 1 in each first of all, then double up. So if I have 3, 1, 2, 3, well, guess what? I have 3 unpaired electrons. There we go. Hey, so that's not too bad. And then let's write the condensed electron configuration for a couple of more here. So let's look at cobalt and tellurium. So number 27, number 52, if you want. You could pause the video right now and try those if you like. And if you had a chance to do that, so cobalt, which is atomic number 27, which is, let's see, 3, 4, 5, 6, 7. So it's 1, 2, 3, 4, 5, 6, 7. Right here is where it is. Cobalt, I think you'll see, is right here. So the noble gas that occurs directly before it is argon. So I'd start off with argon's configuration. And in the assignment that I have you do some of the condensed ones, plus I have you go right from the start. 1s2, 2s2. So yeah, realize that doing the noble gas one is a shorthand. So argon, and then let's see, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 3d7. There we go. How easy is that? And then tellurium, number 52. Let's see, where does 52 fall? It's right kitty corner to bismuth, so it's right here. Tellurium, you would see. And let's see, the noble gas that's right before it is krypton, which is up here. So krypton's configuration, and then moving from there. So krypton, then 5s2, 4d10. Let's see, so 5s2, 4d10, and then 4p, 1, 2, 3, 4. 5, that's actually 5. 5p4. So perfect. You have these labels on your pink periodic table. Man, oh man, we could do this quite easily. So there we go. Now, lastly here, anomalous configurations. Yeah, I said there are some exceptions to the rule, of course. We'll take a look at a couple. The electron configurations of certain elements appear to violate the rules. For example, if I look at chromium, chromium is right here. 1, 2, 3, 4. It's right here. At let's see, it ends at 3d4. Okay, but it has. So we'd expect it to be. We would expect it to be so argon. Let's see, 4s2. So this is chromium. 3d, 1, 2, 3, 4. We'd expect it to be that. 4s2, 3d10. But look at what it actually is. It actually is argon 4s1, 3d5, rather than my 4s2, 3d4. Interesting. And also we have, let's see, what's another one here? We have copper, which is over here. We'd expect it to end in, let's see, 3s2, 3d9, because it's one less. But it actually is 4s1, 3d10. So take a look. Why does it do that? So we'd see that there's exceptions for these ones and these ones in the group 4 and the group 9. If we take a look here, why? This anomalous behavior is a consequence of the closeness of the 3d and the 4s orbitals. It frequently occurs when there are enough okay, let's highlight this. When there are enough electrons to form precisely half-filled sets of degenerate orbitals, or a completely filled d, we will do this. There are a few similar cases among heavier transition elements filled with 4d or 5d, and among the F block. The F block gets really wacky. But if we could take a look here, if you take a look, so 4s1, or sorry, the chromium was supposed to be 4s2, 3d4, but if we take one of these electrons and move it to here, then we have a d5, because remember, d can hold up to 10, so if I have d5, it's half full. And my 4s2 becomes an s1, which is going to be half filled and then fully filled. That's more stable than having this fully filled and this kind of like 4/10 fold. And the same thing with copper. Rather than having 4s2, 3d9, hey, take one from here, you'll become a d10 completely full, and I'll become half full. So if you can make a half full and a full level, that will predominate. So that occurs here in the d4 region. They tend to have d5 and 1s. And then over here, one of those s electrons go here to make it become a full 3d level. Hey, that's it, ladies and gentlemen. So you should be able to do the assignment. And in some of the assignment questions, I ask for the shorthand noble gas notation for electron configurations. And sometimes I ask for the complete one, starting with 1s2, 2s2, 2p6. And once you've done that, you should have a good handle on this. All right, we'll see you again.